Hello everyone, welcome to my YouTube channel. Today we will learn about how to design the pad footing when we have axial load and moment. The first things we have to do that in here we have two things. One is called axial load and another is called moment. The first things we have to list down all the informations that we can call it as specification. The first things we will write down the axial load that will be given 1500, then the moment 50 kilonewton meter. Concrete, for concrete it is usually 13 newton per millimeter square value. Reinforcement for 500 newton per millimeter square value. Then after that we have the design years, that how many years we are going to design it. It will be 50 years. After that we are going to choose the class exposure XC3 that we will get from the Eurocode, because we are designing based on the Eurocode. So that's why we are also following the class that mentioned by Eurocode. After that we have the diameter 12 millimeter, column size 250 and 300. So from this size we can understand that column is a rectangular column, right? Yes, 250 and 300. 50 millimeter. Then bar capacity is 100 and bearing capacity is 150 kilonewton. Okay, the first things we are going to do, which is called the durability and bond requirements. Okay, as per the suggestion from Eurocode, C mini B equal 12 millimeter, which is called the minimum cover regards to the bond will be, which will be 12 millimeter. Then the minimum cover with regards to durability will be 25 millimeter. Then allowance in design for deviations, which will be 10 millimeter. We can take 10 millimeter usually. Then after that we have a formula which is called nominal cover. So minimum nominal cover, how you get, we just add up the durability's value plus the deviations value, we will get the nominal cover. In this case we will use 35 millimeter, our nominal cover. And nominal cover is important because it will use in different steps, so that's why make sure that this value will be correct. All right, then after that, after the sizing, after the first things was to do the specification. Second thing was to calculate durability and bond requirements. After that we are going to do the choose the size. Okay, so before choosing the size we have to make sure that how much load we have, moment, and the that how much load actually we can assume as a self weight of the footing. So let's say in here the service load is 1500, then the moment is 50 kilonewton, then design load is 10%. So we are assuming that the self weight of the footing will be 10% of service load. After that, this is the W. Okay, so the 10%, okay, with the service load, so we will get 107 kilonewton. Because why we need it, because we are going to calculate the area that require for the footings that we are going to build. So there is a two formula that you can use here. One formula is like this: A equal N plus W divided by bearing capacity, which is called 150. In this case that is giving already. So our N is 171 because we divided by the factor 1.4 though, so they will mention the factor also. So 1.4 in the questions, it will be mentioned that how much will be your factors and how much factors you will divided by your service load. So then it will be 1771 plus our W is 107.1 divided by 150. If we do the calculation, we will get 1071 plus 107.1 divided by 150. We will get 7.85 meter square, exactly the same area that you will get. So you can use any formula, this one or this one is no problem. So it will be a similar. So our area required for this footing is 7.8 millimeter, 8 meter square or square meter. So we will take B as 2.80, H we will take 3.5, and then our H is 0.6 meter 65. Okay, so now if we calculate the B and H, so we will get actually the area, right? Okay, so once you get the area, so what will happen in this case? We have to find out the self weight. So our self weight will be multiplied with the new area, right? So 25 times 9.8 per times the 0.65, then we will get the self weight. After that, once you get the self weight, the next steps will be moment. So how we find out the moment? We'll basically, there is a common formula for getting moment, which is bh cube divided 12. So in this case, b we select 2.80, h is our 3.5, then cube divided power of cube divided 12, so we will get 10 meter power 4, because as it is moment inertia, right? Moment of inertia. Okay, inertia. Okay, after that we have to find out the y. What will be y will be half of your height h. So our h is in this case 3.50, we divided by 2, we will get 1.75. That's all. So once we found all those informations, now we have to use one formula. Okay, maximum soil pressure. So how much pressure we will get from this footing, and how much pressure already giving. 150 is our limits. Okay, so our value should be less than 150, otherwise it will be it will fail, right? So there is a formula which is called P equal N plus W divided A plus My by I. So N means the load, axial load, that we already convert to convert by 1.4, right? I mean number factor. Then W is equal to 159, the self weight. Then M is the moment 36 that we already got, and Y already got 1.75. How? Because 3.50 divided by 2, 1.75. Once you get it, we have the area 9.80. I moment of inertia is 10. If we just do the calculation, we will get 131.81. We will just round up to the nearest whole number, which is called 132. And this 132 will less than 150, because this pressure can occur, but we have 150, so our design is accurately is going. So no problem about the maximum soil pressure, no issue about the soil pressure. Okay, all right. So if I summarize the size part, so the first important things you have to know this part. Okay, so for the analysis part, for the size part, we are going to find out the maximum soil pressure. Okay, because if you remember this formula, then you will know that how many input you need to get this output. Okay, let's say you have to find out the N, you have to find out the W, you have to find out the A, you have to find out the M, you have to find out the Y, you have to find out the I. So you will not forget the steps when you will going to design. Okay, so this is the tips that you can apply. So the P equal N plus W divided A plus My divided I. So the first things I will find out N, then W, then A, then M, then Y, then I. So once I found all those informations, I just plug in the informations in this equation, and I will get the maximum soil pressure, which will be less than 150. Okay, once we finish the sizing, now the main important things we have, which is called analysis. Okay, in the analysis part, what we are going to do, we are going to find the ultimate soil pressure. So what is the formula for ultimate pressure? For the ultimate pressure formula, we have N divided A. So already we know the N, right? So N is 150 kilonewton, that is called axial load. Okay, axial load. Okay, then A is the area that already we get based on our selection of size, so which is 9.80, because 2.80 times 3.50. After that we have the M. So M is the moment that is already given, and 50 kilonewton. Okay, remember, ultimate soil pressure, we are using the original value that already given, not the converted by factor. Okay, so our Y is 1.75, then I is 10. So if we do plus and minus, addition and subtraction, this equation, we will get what it called the ultimate soil pressure respectively, and minimum and maximum. Okay, so once we get it, now we have to draw. So let's say for this point is a maximum and this point is minimum. All right, so once we draw this one, now we have to find out moment. Okay, so there is two moment based on the axis, so x axis and y axis. So for the axis, so we have to find out the 154. How we get the 154 kilonewton per newton meter square? Okay, there is a very easy formula that you can apply. Okay, let's say we were going to using the proportional triangles method, but here I am going to make it short for you, that you can apply it easily and remember it. So the our minimum value is 144 plus, okay, from here to here, because we are going to follow this distance, right? So 1.75 plus 0.3 until the point there we are going to find out the pressure. So we are going to find out the pressure here. So from here to here the distance is 1.575 plus 0.35 divided, our whole distance is 3.5, right, times the differences between the maximum value and the minimum value. It will be 17.5. If we do calculations, do the equation, we will get 154. So 154, this is the easy way that you can follow. For the next one, we are going to follow the middle part, so that's why we just add up these two value, 144 and 162, we will get 153. So based on those two value, we are going to calculate our mx and my. So for our mx value, we have to find out the 154 times, okay, how much is the distance from here to here? 1.577 divided by 2 plus minimum value and maximum value times 1.57 divided 2 times 1.57 times 2 divided 3. We will get 197, and for x-axis we are taking 2.80 value that we got from the B. Okay, then my value. So for my value, we have to multiply with 153 with 1.275. So where I get this 1.257? Okay, let's say from here to here our total value is 2.8, right? Okay, I subtract with how much? I subtract with the 0.25, this value, right? So if I subtract this value, I will get the rest of the value will be 2.55. So 2.55, if I divide it by 2, then I will easily get 1.275 for this part. Okay, after that, so once we finish the moment, then our analysis part is finished. So if I summarize the analysis part, the first things we have to get the ultimate soil pressure. So by using the formula for ultimate soil pressure, we will get the maximum value and the minimum value. And once we get the minimum and maximum value, we have to use the proportional triangles to get another two pressure based on the distance. Okay, so we will get the mx and my y-axis and x-axis moment we will get. So once we get the moment, then our analyzing part has done. Okay, so after that we will go for main reinforcement. So for the main reinforcement, the first steps, we have to find out the effective depth. So what is the formula for the effective depth? We have the formula for effective depth, which is h minus c minus 0.5 times the bar diameter. Okay, so h is the 650 that we get when we assume our area, right? That time you can see that h equals 0.65. So that from here I got 650 millimeter. Our nominal cover that we found from the beginning, 35 millimeter. Then our bar diameter is 12 millimeter. So once we get it all those value, if we plug in the equations, we will get 609 millimeter. Once we get it, after that we have to find out the dy. In the same way we will get the dx and dy. Once we finish, the easy part is to do it. We have to divide it into x-axis and y-axis. So x-axis will be the longitudinal bar. So from here we can just use the formula kzas. As mean as max. Okay, so sorry, as max here. So the first things we have to find out the k. So what is the formula for k? K formula is m over fck bd square. So when we are going to take the x-axis longitudinal bar, so we will get the our b equal 2800 millimeter. So all those value in millimeter, so that's why I'm going to convert all those value into millimeter. So after that our d will be 609. Okay, so 609 is my dx. Okay, because we are going to find out the x-axis, so we will use the dx. Okay, after that we have to find out the z. So for the z value we will just plug in all those value into this equation, and we will get the 0.98. so we will take the smallest one, 0.95d. So once we get it, next formula is as. So mzas. So m formula, okay, in the m formula how many input we have to use? Then we have to m already got. Where we get it? Because it is m axis, right? We are going to find out the x axis, so that's why I'm going to take the m axis, and that one you can get from our analysis part. Okay, after that we will get as mean, as max. So this is a very basic form, calculations part, so that's why I'm skipping all those calculations part. You can do it. After that we have the transverse yy direction. The same things for the yy direction. Our b will be 3500. Our d will be dy, and remaining all those value will be will same. Okay, so there is no problem about it. So maximum value and minimum value. So once we get it, we have to choose the bar spacing. Okay, after that we are once we finish the main reinforcement, we will move to the shear. Okay, for shear we have to have three types of things we have to find out. First things, which is vertical shear. Okay, so for the vertical shear is at 1.0d. so from here to here the distance is how much? Our d is 609. Okay, from where I get it from dx, right? So if I convert it into the meter, I will get this 0.609. Okay, once I get it 0.609, I will use it. So from here to here the total distance is 3.50, right? If I subtract the 0.60 from here to here, we have 1.575. so if this value is 0.609, so my remaining value will be just from the subtraction value. So 1.575 minus 0.609, because we are going to find out the vertical shear from the column face at 1.0d. So then we will get the 0.97. so if you want to make it round number, so you can make it 0.97, no problem about it. So once we get it, we have to find out the active pressure at critical section. So the same things now we will find out in previously I showed you that how you get 154. So in this case, active pressure at critical section we get like this, the minimum value 144. so until which point you are going to find out? You're going to find out until the critical section, right? So your critical section's distance is 3.02. actually the value will be 3.015. I just round up to the nearest number. So I take the 3.02 divided, the full length is 3.50 times the distance differences between the minimum and the maximum pressure. Once I will do it, I will get it 159 kilonewton per meter square. So once I get the active pressure, by using this active pressure I can get the shear. Just I multiply with the area, sorry, I just multiply with the 2.8, which is my b, and 0.97, which is this distance. Okay, if I just multiply, I will get the shear. Okay, so now we have to do the bar extended beyond the critical section. We have 966 times our nominal cover is 335. We will get 931 millimeter. So we have the one formula which is 36 bar plus d. So 36, our bar diameter is 12, plus d will be 609. So we will get actually 1041. So which is more value, so that's why we will take a 60 millimeter square. After that we have the k value. So we have a flow that k p1. Once you get the k p1, and then we just plug those value into the equation. So this is the equation for getting the VRDC. So once you get the VRDC, then we will move to the V mean value. So for the V mean value we have the equations. The k value is 1.57, that I just get it from the previous equation, and FCK value is 30, I power 1.2, my B and D value 2800 and 609. Once I get it, I will get 6643 kilonewton. Okay, I make newton to kilonewton, so I will get 643, which is more than my VED. So that's mean my design is okay for the vertical shear at 1 point D from the column face. Okay, so now you will move to the punching shear. For the punching shear we have 2.0 D from the column face. So the total effective distance was how much? So 609 and 57, we will get it. So from here we have to find out the average one. So my average D is 603 millimeter. Okay, so once I get it, I have to find out the control perimeter. So I will get the control perimeter 2 times 350 plus this 250, then times, this is like a circle, so the 2 pi r. Okay, so after we get it, we will get the control perimeter. We will multiply those value, do the solve the equation, then we will get the area. So our area is area within perimeter. So how many area we can see here? 1 2 3 4, right? So we just do like this: 1 area, 2 area, 3 area, and 4 area. We add up all those area by using the areas formula based on the shape that we are going to use in our footing. Okay, so after that we will get the area. So now we have to subtract this area from our active pressure, and 2.8 times 3.50 is the area. So we will get actually the 566.1 kilonewton is our average shear force at control perimeter. So now we have to compare the maximum value and the minimum value based on this shear. Okay, for doing this one, we have to find out the punching shear strengths. There is a formula: VED equal beta VED divided UD. So my U is a control perimeter, my D is a 603. Okay, so VED already I got, but I don't have the beta. So getting the beta value, I have to use this formula. But when I'm going to use this formula, I also need the W1 value. So first I need the K value also. So the K value, how you get? 0.6, right? So how I get it? Let's say the first things we have to divided the C1 and C2 value, 350 and 250. Okay, the column dimension you have to divide it, and then you will get 1.4. And if you go to the books that we are going to use for the designing, so you will get 325 pages, table 6.1. okay, table 6.1. So based on this value, our nearest K value will be 0.6. we can select from here. After that, so once I get the K, okay, another formula I need, another value I need to complete this beta value, so which will be W1. So my W1 value will be 0.561 square C1 4C 2D 16D square 2 pi D C1. So I just plug in those value, I will get 7.89 times 10 power 6. So if I get this value, so if I plug in those value in here, K value it was unknown, W1 value was unknown, so I already found those value and I will plug in this equation. I will get 1.06. after that I will do the I just plug in all those value. Now the new equation, my punching shear stress will be 0.11 Newton per meter square. So my V mean, so V mean got the formula. It's a very simple things that we just need to plug in all those value, then we can easily get it. After that we have the maximum punching shear, it is same as 2.0D. we have to find out the VED. Already got 1500 from the original Axial load that already given. So we have to find out the U naught, then we have to find out the W, then beta, then K also will be 0.6 for the same cases here, so no need to find out the beta for these cases. Okay, I mean the K, so K will be 0.6. so once we get all those value, we will just plug in all those value into the beta equation. Once we get the beta, then we will just solve this equation and our value will be 2.40. so once we get the VED, we need to check the maximum value also. So the minimum value also. So the minimum shear will be how much? So 0.6, there is a formula, it is 0.6 times 0.6 0.5 times 0.6 1.1 minus FCK 250 is a formula from Eurocode. Okay, Eurocode, we just following our design from based on the Eurocode. So that's why we also can use this formula from the Eurocode. So we just plug in the value. FCK is a 30, FCK is 30, just we will get 5.22, which is more than our punching shear at maximum punching shear. Okay, so this value is more, so I can conclude my design is okay until maximum shear. So after that we have to do the cracking one. So later I will show it to you. Thank you so much for your time.